Okay, in this video we are talking about measurement, units, precision, accuracy, and significant figures. The term SI units, SI, refers to the International System of Units, or in French, Le Système International d'Unité. And there are 7 of these so-called SI base units. These are base units for things such as length, mass, time, amount of substance, temperature, electric current, and luminous intensity. So again, take a look at these 7 base units. And of course there are a lot more units in the world of science than these 7, but everything else can be considered a derived unit that can come back to these. So derived units would look like the following. For example, area would be the square meter. Volume is the cubic meter. Speed is meters per second. Frequency is hertz, which is also known as 1/seconds or inverse seconds. Density, in terms of the kilogram and the cubic meter, would be kilograms per cubic meter. Force is newtons, which would be defined as mass times acceleration, kilogram meter per second squared. And pressure, the Pascal, would be defined as force divided by area, so kilogram per meter second squared. Now there are many other units besides these, and there are typically some non-SI units that are frequently encountered in chemistry. So for example, volume would typically be in liters or possibly milliliters or microliters. Temperature is typically in degrees Celsius, and there is a conversion factor to go from Celsius to Kelvin. Energy is sometimes in either calories or joules. Units of concentration can be in moles per liter, or you might have grams per liter, or possibly some kind of percentage based on mass or volume. Pressure, besides in pascals, can also be either in atmospheres or in millimeters of mercury. So just to give you an idea of some other units that are available for you in chemistry. There are 2 prefixes that I would like you to know that will make the base unit larger. Mega increases the base unit by a factor of 1,000,000. So for example, a megahertz would be 1,000,000 hertz. And kilo increases the base unit by a factor of 1,000. So for example, a kilometer would be 1,000 meters. There are many metric prefixes that will make the base unit smaller, and these include deci, centi, milli, micro, nano, and pico. All of these will make the base unit smaller. So for example, a decimeter is 1/10 of a meter, a centigram would be 1/100th of a gram, a millimole would be 1/1000th of a mole, a microliter would be 1/1,000,000th of a liter, and nano and pico the same thing. That would be 1/1000,000th and 1/1,000,000th as a small fraction. So now on to a distinction between precision and accuracy. These words are often used interchangeably in everyday experiences about being precise and being accurate. Of course, in science class, it'd be nice to be both precise and accurate with your measurements, but sometimes what happens when you're taking a set of data is you might be precise, but you aren't not necessarily accurate. So here's the difference. Precision refers to how close a series of measurements are to each other, and accuracy refers to how close a measured value is to the accepted value. In this example, if these darts represent precision, they are close to each other, but they are not close to the bullseye. So they would be precise, but not accurate. This example would be not only precision, but also accuracy as well. And this is what we shoot for in chemistry. We're trying to be both precise and accurate. Now to talk about measurement and move into significant figures. Anytime we take a measurement, there is always some amount of uncertainty, and that would be found with the final digit in the measurement. So in this case, a measurement of 6.1 centimeters, the 1 represents the estimated digit. If that pencil, instead of being just beyond the line or just short of the line, if that pencil were exactly on the line, then you would need to still add a 0 at the end to indicate the final estimated digit. And I'd like to make a distinction between the number 6 and the number 6.0 when it comes to measurements. So in this ruler, where there are only two lines, one at 0 centimeters and one at 10 centimeters, to record the length of the pencil, you could say maybe 6 or 7, but you could not say 6.5. And that's because every line on this ruler is worth 10 centimeters, so we can only estimate to the ones place. That's kind of a silly ruler, so let's look at a more conventional ruler that actually has more lines on it. Alright, now on this ruler, we might say that the measurement is between 6 and 7, possibly 6.7 or 6.8. The final digit is the estimated digit. We could not say 6.75, and the reason for that is because we can only go 1 power of 10 smaller than what the lines are worth on the ruler. So we could estimate to the 10th place. If you wanted to estimate to the 100th place, you would have to have a ruler where every line was on the 10th. So for example, every line on this ruler is worth 1/10 of a centimeter. As I zoom in closer, you can see that this particular length would fall somewhere between 6.7 and 6.8. So your estimated digit would be possibly 6.76 or 6.77, and so each line is worth 0.1 centimeter on the ruler, so we estimate to the 100th place. Now, if you had a pencil that was exactly on the line in these two examples, comparing the top ruler with the middle and the bottom, the first measurement would be 6, but that's all you could say. The second measurement, because it's on the line, we could say 6.0. And the third measurement is also on the line, but now we are going to the 100th place. And 6.00 is the most precise measurement of these three. Even though mathematically they all mean 6, scientifically, in terms of measurements, 6.00 is more precise. And significant figures, or sig figs for short, include all of the known digits in a measurement plus one estimated digit. In this example, 6.7 has two significant figures. A number that would be 6.70 has three significant figures because we include the 6, the 7, and now the final estimated digit. So 6.70 is more precise than 6.7. It has more sig figs, so it is a more precise measurement. Alright, let's talk about some rules for determining the number of sig figs in a measurement. We are not going to talk about exact numbers in this video because exact numbers, counting numbers, have unlimited number of sig figs. We're focusing on measurements here. Measurements typically are going to come with a certain degree of uncertainty. The first rule for determining the number of sig figs in a measurement is that non-zero numbers are significant. So if you have the numbers from 1 through 9, they will always count. In this case, the measurement of 72.3 grams has 3 sig figs. Sig fig rule number 2, captive zeros are significant. And these are the zeros that occur in between non-zero digits. So the two zeros in the middle of the 8 and the 4 are considered significant, and 800.4 centimeters has 4 sig figs. Rule number 3. If you have a decimal point, then any zeros at the end of the number, so-called trailing zeros, are significant. So if a measurement of 1.000 seconds was given, that measurement has 4 sig figs. Sig fig rule number 4, if there are no decimal points in the number, then the trailing zeros do not count as significant. So 500 does not have a decimal. Therefore, this measurement of 500 liters would only have 1 sig fig. And then finally, sig fig rule number 5, if there are any leading zeros in a number, so typically for a number that's less than 1, any leading zeros are not significant. In this case, 0.0075 meters has 2 sig figs. So now what I'd like you to do to see if you understand these rules is to sort the following 12 measurements into 4 categories based on how many sig figs they have. All of the following measurements will have either 1, 2, 3, or 4 sig figs. If you need to slow down, rewind, pause, watch the video again to see examples, or if you need to refer to other resources to help you understand significant figures, you're welcome to do that. But on the following slide, you're going to see 12 numbers, and then you'll have to answer the questions that are given to you on this Google form. So here are the 12 measurements, and all of these measurements will have either 1, 2, 3, or 4 sig figs. It's your job to decide how many significant figures they have, and then again you'll submit your answers to the questions on the Google form. Alright, that's it. Thanks for watching.